And we're back. Well, let's hope that the candy bar I ate while I took a break will get us through this presentation. It's going to be a little bit technical, a little bit algebraic. That is probably to be expected if you've worked with Laplace transforms before, because those partial fraction decompositions that you typically have to do when you do a Laplace transform by hand and with tables, that can get rather epic. And well, that means that if we get something that allows us to handle more complicated things or handle the same things, um, unless somebody kept information away from us in a nefarious way, the effort should still be appreciable, and that will be the case here also. So let's take a look. The Laplace transform of a function f on the positive real line is f of s being the integral from 0 to infinity f of t e to negative st. That's a definition that comes, for example, out of the differential equations course where people typically work with these things. And a theorem from complex analysis actually is that under fairly general conditions, whatever that means, we obtain that the function can be obtained from the Laplace transform as 1 over 2 pi I times the limit as r goes to infinity of the integral from gamma minus IR to gamma plus IR, Laplace transform times e to the st ds, which is 1 over 2 pi I times the principal value of the integral from gamma minus I infinity to gamma plus I infinity, f of s e to the st ds, where gamma is so that all the singularities of f lie to the left of the vertical line x equals gamma. Now we're going to draw that a little bit. We're going to visualize that in a little bit, but that is a very powerful theorem, and the proof we're actually going to omit. Yay! Well, okay, maybe not hooray after all. I mean, on one hand, yes, the proof is very complicated, and I think the only way I could piece one together would be to quote some other very deep results about how to invert Fourier transforms, and those results take a while to prove, so that's the reason why we're going to omit those here. But at the same time, we've done mathematics at this level often enough to now realize, yeah, okay, so we're dodging a bullet, but at the same time, I think we're back to those, or we are now really acquiring these reflexes that we want to have a proof for something. Well, so here, we're skipping one. All right. If basically this is a theorem now, how do we compute those Laplace transforms? Well, suppose that our function f has n singularities as 1 through Sn that are all to the left of x equals gamma, and we want there to be an r0 so that for all r greater than r0 we have that the absolute value of f of s is smaller than a value mr on the left half cl gamma r of the circle. Well, and it's got all this stuff attached to it because it's a circle around gamma of radius r, and we want to have the left half, which is what's indicated by that L up here. So it's supposed to be bounded by that, and so that these m sub r's go to 0 as r goes to infinity. Then f of t is the sum of the residues at the s equals s sub n of the function e to the st f of s for all t greater than 0. How does that go? Well, e to the st f of s is the function for which we have to compute that integral along a vertical line, right? And that thing, because e to the st is analytic, has singularities where f has singularities. So those singularities are sitting somewhere like this, and they may be symmetric or maybe not. And then we've got this vertical line, and we do know that the integral along this vertical line plus the integral along this semicircle, that's going to be this sum here. And then if, and that's something we've done with the calculus of residues now several times, if we now let this time vertical line segment approach the full vertical line, and if we let the radius of the circle go to infinity, as long as in some fashion we can get rid of that integral along the semicircle, we get that this sum will be the integral along the vertical line. So that is something that shouldn't be terribly new to us anymore, and we can work our way through it too, because we know from that previous theorem that we're just going to quote that f of t is 1 over 2 pi I times the limit as r goes to infinity, gamma minus ir to gamma plus ir f of s e to the st ds. And that's the sum of all those residues, minus 1 over 2 pi I times the limit as r goes to infinity of the integral of the function over this left half of the circle of radius r around gamma. But now, we look at that integral in absolute values, and well, we just parameterize it. And if we integrate along a left half, that would mean our theta goes from pi halves to 3 pi halves. And we just stick in a parameterization. F of gamma plus r e to the I theta, e to the gamma plus r e to the I theta t from here. And then, of course, we have to take the derivative with respect to theta, which is ri e to the I theta d theta. I think now we push the absolute value inside. Yes, we do. And that, of course, is not equal. That's a less than or equal. All right, and we're back. That's less than or equal because we're using the triangular inequality for integrals. And now the f is bounded by mr. The ri e to the I theta, well, this stuff here has absolute value 1, so that just gives us r. And what's left is, if we puzzle the exponential apart, is e to the gamma t, e to the r cosine theta times t. And e to the gamma t, well, gamma is a positive real number, t is a real number. And so that means that this becomes mr e to the gamma t, and then we've got this other integral left. And here I've done a little bit of an index shift, because the cosine function from pi halves to 3 pi halves, that's a lower half wave of a harmonic oscillation. So that is the same as the negative sine function from 0 to pi. Let's see, the way you do that is you go with theta minus pi halves plus pi halves, and then use a substitution as well as the appropriate trig identities, or you do it geometrically as I just mentioned. And this thing now is something we can apply Jordan's inequality to, and that's something, of course, that you probably want to look up at this stage. But what Jordan's inequality allows us to do is it allows us to say that this integral is less than or equal than pi over rt. Everything else stays the same. Now this r, of course, goes away with this r. So this is mr times something that depends on gamma and on t. But remember, gamma and t are both fixed. And that means as r goes to infinity with mr going to 0, that means that this stuff all goes to 0. Okay, so that establishes the equation. And that's it. Well, at least in terms of proofs. Because now we have to look at how this theorem is being applied. But it sounds kind of attractive, basically, when you want to find an inverse Laplace transform. Rather than doing partial fraction decompositions, you can just, quote unquote, compute residues. Let's see how this goes. Let's take the inverse Laplace transform of s over s minus 1 times s squared plus 2s plus 2. So this is one where this thing has two complex zeros. And so that's a partial fraction decomposition. If we were to do it that way, that actually gets kind of nasty. All right, so the singularities are at s equals 1 and at, well, negative 2 plus minus square root 2 b squared, 2 squared, 4 minus 4ac, 8 divided by 2, which is, of course, negative 1 square root of negative 4 is negative 2, is 2i, and then 2i divided by 2 is I, so negative 1 plus minus I here. And all singularities are simple poles. And we also know that f will go to 0 as s minus 2 goes to 0. We're going to use 2 as s minus 2 goes to infinity, so we're going to use 2 as our center point there. And so for the boundedness condition with gamma equals 2, we can obtain the following. We now need to somehow show that as s minus 2 goes to infinity, this whole thing is just bounded by a single number, right? We can see, because we're dividing by stuff, that f goes to 0, but f doesn't just have to go to 0, it has to go to 0 uniformly on those contours. Everything has to be bounded by this m sub r. So how are we going to do this? We're going to first, of course, factor. Sure, I mean that's like a good idea. And so that's just the factorization of the s squared plus 2s plus 2, and we put the absolute values around all the individual factors. And now we expand with plus minus 2. So the numerator is s minus 2 plus 2 absolute value. The denominator is s minus 2 minus negative 1, and here s minus 2 minus negative 3 plus I, and s minus 2 minus negative 3 minus I. Well, that is just expansion with plus minus 2. And now, well, now we have to use the triangular inequality. We're going to use the regular triangular inequality in the numerator, and we have to use the reverse triangular inequality in the denominator, right? Because you make a fraction larger by making the numerator larger and the denominator smaller. So that means the numerator is smaller or equal than s minus 2 absolute value plus 2, regular triangular inequality. The denominator is greater than or equal, and therefore the whole thing is less than or equal, then s minus 2 absolute value minus negative 1 absolute value plus s minus 2 absolute value minus negative 3 plus I absolute value times s minus 2 absolute value minus negative 3 minus I absolute value. We've got negative signs here, here, and here. And then we're just straight using the reverse triangular inequality. And now we know that this is if you have a certain distance, if s minus 2, of course, is the radius of that circle, then that is r plus 2 divided by r minus 1 absolute value, r minus root 10, and r minus root 10, as r goes to infinity, that goes to 0 because you've got r divided by something on the order of r cubed. So we do have a uniform bound for the function on that left half circle that does go to 0. And well, now we compute the residues. So the residue at 1 of e to the s times f of s, or e to the st times f of s. It's important to keep the exponential in there. Well, that is because this is a simple pole. It's just the value of the function with the factor that makes it a simple pole discarded, right? So it's e to the st times s divided by s squared plus 2s plus 2 at s equals 1, and that's e to the t over 5. So that's really quick. That's really simple. That's a lot simpler than what we would do with partial fraction decompositions and all the other stuff. But remember, you would always have to do those inequalities. So there is a certain preservation of energy going on. Then we have the residue at negative 1 plus I, which was one of the zeros. And we do the same thing. We just suppress the term that makes negative 1 plus I a simple pole and look at the rest. And we just plug in s being equal to negative 1 plus I. Of course, this one is more complicated. We get some cancellation here, but I think we'll just work it out from here. Okay, so we get negative 1 plus I times t gives us the e to the negative t plus it, sure. Negative 1 plus I is just copied. Then we have negative 1 plus I minus 1, that's negative 2 plus I. And negative 1 plus I plus 1 plus I, that's just 2I. Okay, and then we simplify that a little bit. We leave the numerator as is, multiply out the denominator. We get negative 2 because I times 2I is negative 2. And then we have minus 4I from the negative 2 times the 2I. And now we expand with negative 2 plus 4I to get a real denominator. And so that would be e to the t plus it. That, of course, doesn't change. The denominator will be 2 squared plus 4 squared, which is 4 plus 16, which is 20. And if you multiply those out, you get negative 2 times negative 1, which is 2. And I times 4i is negative 4, so you end up with negative 2 as the real part, right? Negative 2 times I plus 4i times negative 1 gives you negative 6i, so that works out. And then, well, we just break that up. That is negative 1/10 minus 3/10 I times e to the t plus it. And the residue at s equals negative 1 minus I, well, same story. We're suppressing the term that makes negative 1 minus I a simple pole, and we plug the number into what's left. And it's very similar to what's done on the previous panel. It's e to the negative t minus it times negative 1 minus I. Then we have negative 1 minus 1, negative 2 minus I. Negative 1 plus 1 goes away, so we get minus 2I as the other term. Again, we multiply things out, so we leave the numerator as is. We get negative 2I times I is 3 negatives, so yeah, it's still negative 2. And then negative 2 times negative 2I is plus 4I. Again, we multiply with the conjugate, which means, again, the exponential stays as is. The denominator is 20. Then we get negative 2 times 1 times negative 1, which is 2. Negative I times negative 4I gives us negative 4. 2 minus 4 is negative 2. and we have negative 2 times negative I is 2I, negative 4I times negative 1 is 4I, so that adds up to 6I, and that's what we've got there. And again, that's negative 1/10 plus 3/10 I e to the t minus it. And now that means that f of t is e to the t over 5 plus the residue on the first plus the residue on the second. And, well, this is the kind of thing where I think double E's often, or double E's, electrical engineers, often just use the function just like that because they're very comfortable using complex numbers in their circuit analysis. If we want this to actually have a real answer, well, then let's take a look at this, and we realize that this coefficient is the conjugate of this coefficient, and this function actually turns out to be the conjugate of this function. That may be a little bit surprising, but e to the negative t is real, and e to the it is the conjugate of e to the negative it. And because the product of conjugates is just the conjugate of the products, that means that we actually have a term and we add to it its conjugate. So that means that this is e to the t over 5 plus twice the real part of what we have out front here. And what is the real part? Well, this thing becomes e to the negative t cosine t plus I sine t. So we end up with, well, we keep the e to the t over 5. Then we have 2 times negative 1/10. Well, that ends up being negative 1/5. And then we have the real part of this, which is e to the negative t cosine t. And then we have to look at the imaginary part of this thing, and that's going to be multiplied with this, so it's going to give us a 3/5. And then we have a negative sign here, but remember the I times I is another negative, so it becomes positive. And the imaginary part of e to the negative t plus it is e to the negative t sine t, so that's really what comes out of that. And that is something that should be quite familiar, because this is the kind of thing, if you've done this a couple of times in your differential equations class and the memory is still fresh, then you can say, yeah, that feels about right. That's what it should be. And, well, and of course it also is. You can double check. Okay, so that means that these formulas allow us to do the computations that we've done with tables before differently. As I mentioned before, if you really need a Laplace transform and you just need the transform and not the way how to get the transform, I would use a computer. But there are situations where things might actually get so bad that if you want to find the inverse Laplace transform of a function like hyperbolic sine of as divided by s squared over hyperbolic cosine of s, where 0 is smaller, a is smaller than 1, you might not be able to find that in a table. Okay, now don't nail me down on that. I haven't tried this in a computer and I haven't looked for it in a table, but it's quite nasty. Okay, so what can we do here? Well, it's a good exercise in, again, using the residue theorem and the theorem that led to this inversion theorem for the Laplace transform. We find the singularities there at s equals 0, where we've got a pole of order 2, and at s equals I times pi over 2 plus pi n. That's something that we know about the hyperbolic cosine function, right? The hyperbolic cosine function is related to the regular cosine function in that you stick an extra I in the argument, and then you have to make sure that everything else works out. And so that means that the zeros of the regular cosine function, which are of the form pi halves plus pi times n, where n is an integer, are moved to the imaginary axis. And yeah, that's with n being an integer here. And those are all simple poles, and that is because the zeros of the cosine function are simple. Let me think about that. Yes, they are. I was worried there for a moment because the cosine expansion goes with constant plus something that's squared, but that's when you don't expand around a 0. When you expand the cosine around a 0, it looks like a sine function, and that means that the zeros are simple, and that means that the poles, the zeros of the denominator, are simple, and that means that the poles are simple. And I've just, as I was talking my way through that, talked about the cosine. Well, remember, going from the cosine to the hyperbolic cosine just means that certain things move to the imaginary axis. Other than that, everything looks the same. Okay, so we can't apply the theorem directly because the theorem talked about finitely many of these zeros, right? But the integral over the line x equals 1 is the limit of the integrals over the line segments from 1 minus ik pi to 1 plus ik pi. And so if the integrals over the left halves L of circles s minus 1 absolute value equals k pi converge to 0, and if the sum of the residues converges, then we're okay. So the idea is that we've got on one hand this singularity at the origin, and then we have these evenly spaced singularities along the imaginary axis. And we know if we just take a vertical line segment and a semicircle so that we cut through the line that contains all the singularities in such a way that we don't hit any of the singularities, well, we can get hopefully this integral here. And then if we make that contour larger, and if we can somehow convince ourselves that these integrals over the circles go to 0, and that's going to be rather nasty, if we can do that, well, then we in the limit get the integral over this vertical line, and that's the integral that we're actually interested in by the inversion formula for the Laplace transform. Okay, so what we're going to do here is we will first, as mathematicians and scientists often say, formally compute the inverse transform, and that is a reasonable thing to do, because if that formal inverse doesn't make sense, then there is no point in doing the ugly estimate that shows that that inverse works out. So we have to find that inverse formally anyway, and if there's also already something fishy with that, then we might be able to save ourselves the heavy lifting. Now, that's not going to happen here where everything is going to work out, but nonetheless, when something is computational and you're interested in the result of the computation, it's sometimes very reasonable, even, and I'm saying this as a pure mathematician who wants everything proved, signed, sealed, and delivered and all that, it's often very reasonable to just first do the computation pretending as if everything works out just fine. Okay, so if we do that, we need to find the residue of e to the st times our function at 0. And because that is a pole of order 2, we use the theorem that says you have to take the derivative of that function that you obtain after you erase this appropriate part of the denominator, and you take that derivative at 0. Okay, so this time around it's a quotient rule. It's a quotient rule with a product rule, so it gets rather ugly. Derivative of the numerator is derivative of the first t e to the st times the second sinh as, plus derivative of the second a times cosh as times the first e to the st times the denominator cosh s minus the derivative of the denominator, which is sinh of s, times the numerator, which is e to the st sinh as, divided by cosh squared s. And here's where you might think, my God, how am I going to simplify that? Well, the answer is you don't, because what we do know is we're only interested in this thing at s equals 0. So let's plug in s equals 0. We plug in s equals 0, sinh of 0 is 0, which means this term goes away and this term goes away. Cosh of 0 is 1, which means this one becomes 1, this one becomes 1, this one becomes 1, e to the st becomes 1 too. So this ends up being 0 plus a times 1 minus 0 divided by 1 squared. That's just a. And that's great. I wish the other ones would be like that. Unfortunately, they're not that simple, but we'll fight our way through those too. So the residue at s equals I pi over 2 plus pi n of this thing would be the value of, again, we just toss out the part that makes the number a singularity, and because these are simple poles, we just have to evaluate what remains at s equals I pi over 2 plus pi n, so we just stick those numbers in. We get e to the I pi over 2 plus pi n t times sinh ai pi over 2 plus pi n divided by negative pi halves plus pi n quantity squared. The negative is the I squared. Okay, then we simplify that somehow. Well, let me just see what I was doing there. Yeah, right. We use the equation that says that sinh iz is I times sine, negative I, or is I times sine z, because what happened here is we kept the exponential. Okay, so the exponential is exactly the same as what we had up there. This negative sign is this negative sign up front here. The denominator, well, we took out a pi over 2, so we get a pi squared. If you take a pi over 2 out, you end up with a 2n plus 1 here, so that's fine. And the pi over 2, when you square it, of course, gives you a pi squared over 4. The 4 is pushed into the numerator. Good. And then basically sinh iz is I times sine z, so that's where that I comes from. And the sinh becomes sine. That makes things easier to work with because now at least we're on the real line. We've got something that we can deal with. Okay, so now we need to add those residues, and the way I want to do that is I want to look for cancellations between residues that are on points that are on opposite sides of the axis. So let's see. Pi halves plus pi n is the negatives of pi halves plus pi times negative n minus 1, because pi halves minus pi gives you negative pi halves, so this is actually negative pi halves minus pi n. So these are symmetric points across the origin, and I am hoping at this stage that the residues at symmetric points across the origin will somehow add up nicely, which is okay because we're only interested in the principal values. So some kind of cancellation across a symmetry is not a problem at all. Well, okay, take those residues, and yeah, that's what the residues are, right? That's what we had worked out. Straight from the first computation is this first term. Straight from the second computation, only with n replaced by negative n minus 1, we get what we have over here. So this is just straight substitution. Okay, now we still leave the first term as is, and in the second term we just simplify. Pi times negative 1 is negative pi, plus pi halves is negative pi halves. That's the only thing that happened here. Same thing happened here, and here we just puzzled everything apart. 2 times negative n is negative 2n. 2 times negative 1 plus 1 is minus 1. And here's where things get nice. Here's where things get interesting, because now these things start looking startlingly similar, right? So again, we just keep the first one as is, and we realize that here's where we can just pull out a negative sign. So this is e to the negative I, pi over 2 plus pi n times t. So this guy is the conjugate of this guy. This negative sign here can be pulled out of the sine function, turning this negative sign into a plus sign. That keeps this stuff here. And then we have a pi squared over negative 2n minus 1 squared. But if you square a negative sign, that just goes away. So this actually is 2n plus 1 quantity squared. So that means this guy is the negative conjugate of this guy, because this is all real. This is the conjugate of that, and we've got a negative sign in there. So that means that if you subtract the second term's conjugate from the if you subtract the second term's conjugate from the second term, okay, if you subtract the conjugate, that would mean that you end up with the imaginary part. And the imaginary part of that thing is, oh goodness, let me just talk myself through that. There are just too many i's flying around here. This is cosine plus I sine, and the I cosine goes with the negative I cosine, so the cosine goes away. The sine part gets doubled, and then because you have an I here, you end up with an extra negative sign, and that negative sign is being absorbed because we have a sign of a negative argument here. So this is actually cosine minus I sine, and then another subtraction here gives us ultimately that we just get twice the sign of the argument in here, and the 2 is absorbed into the 8, and everything else stays the same. Okay, that one is rather rapid. Be careful as you work your way through that. This one I've double checked, and I'm quite certain that this one is right. Yeah, and that's all I can say here at this stage. It worked out. Okay, So what does that mean for us? That means that the inverse Laplace transform is the residue at 0 plus the sum of all those other residues. And that is the case if indeed all the integrals over those left halves L of semicircles of radius k pi around s equals 1 go to 0. So now we actually have to bite the bullet and do the ugly estimate. And so if we're looking at that integral over this left half of that circle, well, that's again the integral from pi over 2 to 3 pi over 2 of sinh a, and then we just parameterize the circle. It's 1 plus k pi e to the I theta, and that's of course plugged into everything we have in the integral, and then we have the derivative, which is k pi I e to the I theta. Now we use the triangular inequality and puzzle things apart a little bit. And as we do that, well, what do we have? The k pi I e to the I theta, that's just k pi in absolute value because I e to the I theta has size 1. 1 over 1 plus k pi e to the I theta absolute value squared, that's just this term of the denominator. I wanted to keep that separately for our estimate. And then we've got the sinh of the inside as an absolute value, and k pi e to the I theta is k pi cosine theta plus ia k pi sine theta as we multiply that out, and that's the same for both arguments here. And that means, that means we take the k pi out, we take this fraction out. So because 1 plus k pi e to the I theta absolute value squared, that is a number that will always be at least equal to k pi minus 1. And so that means the smallest the denominator can get is k pi minus 1 quantity squared, and so it only gets bigger when we replace the denominator with that. And then we have that the rest is the square root of the sinh squared of all this stuff, and here we used that sinh squared of x plus iy is sinh is bounded by sinh squared, or is even equal to, I think those are equalities for the sinh that you want to look up at this stage, is even equal to sinh squared of the real part plus sine squared of the imaginary part, and similarly we used an equation like that for the cosh squared. Okay, well that now, leave the front alone, that now becomes just square root of 1 over sine squared over sinh squared with the appropriate arguments, and here in the denominator it's 1 plus cosine squared over sinh squared. And that is nice because now if we can show that these terms are sufficiently small, then we're basically integrating something that is bounded by a number 1 plus something, and so then this would just end up being a number, and that's good because then the k over the k squared we have here would make the whole thing go to 0. Okay, so how does that go? Well, we have to distinguish two things. We have to distinguish values of theta where we are still close to those singularities, so those would be values of theta where we are close to the vertical line, and values of theta where we are far away from the real line. So if we're between pi halves plus arc sine 2 over k pi and 3 pi halves minus arc sine 2 over k pi, that's the leftmost part of the circle with a little stub that we have to deal with differently left out, which is the attachment to the vertical line. And for that we have that, well, sinh squared of a times 1 plus k pi cosine theta. Now we have to be very careful here. Well, that is greater than or equal to sinh squared negative a, and that is because we know between pi halves and 3 pi halves we have that the cosine is negative. And so that means what we're getting back here is a negative number that is at the worst negative 2 over k pi, and negative 2 over k pi would give us a times -1 here, and the sinh is an increasing function, and so that means that this will be greater than or equal to sinh squared -a. Give me a second here. Yeah, I had to check myself here for a minute. This is another one of those that you may want to draw out to, but basically this means the largest value that this thing can assume, and remember that negative numbers, of course, large absolute values means they're really small. The largest value this thing can get is -1, otherwise it gets smaller than -1. And that means because sinh squared now actually is sort of like a parabola shape, you're always to the left of -a in the argument, and that means that the sinh squared here is greater or equal than sinh squared -a, and sinh squared of -a is equal to sinh squared of a, because the square of the sinh is an even function. Okay, good. That means that the square root that we had here, that this horribly ugly thing, what can we do with that? Well, we've got denominators here, right? So sinh squared is greater or equal than sinh squared a. So that thing is bounded by 1 plus 1 over sinh squared a, and that's because the sine is less than or equal than 1, the sinh squared is greater or equal than sinh squared a, and this denominator here is greater or equal than 1, so we just drop it. So that's bounded by this number, and that's just a number, and that's all we care about. And for pi halves less than or equal theta less than or equal than pi halves plus arc sine 2 over k pi, and as well as for that other little stub that we had to investigate, we have that the sine of theta is near 1 for large k, and that's because when k is really large, then arc sine of 2 over k pi is near 0. So that means we can find a sequence of integers kj that goes to infinity, so that a times kj pi sine theta is within pi over 4 of an integer multiple of pi. And so that is, we don't really know what a is, right? We only know it's between 0 and 1. But now we have that sine theta is near 1, so that means this is approximately a kj pi, and then if you multiply a with kj, every so often this thing will be within pi over 4 of an integer multiple of pi. And for those kj, the square root, which I this time have written in its original form, is bounded by the square root of 1/2 over 1/2. And that's because, well, the sine squared, if you're within pi over 4 of a multiple of pi, that means that we are less than or equal than sine squared of pi over 4, which is less than or equal than the square of 1/2 root 2, so that's less than or equal than 1/2, and we just drop the sinh squared. And the cosine squared is greater or equal than 1/2, and we also drop the sinh squared here, and that means that this thing is greater or equal than 1/2. The denominator is greater or equal than 1/2, which means numerator smaller or equal to 1/2, denominator greater or equal than 1/2 means the quotient is less than or equal than 1/2 divided by 1/2, and that's of course 1. And that means that the integral, which is this monstrosity here, is bounded by the number out front times the integral from pi halves to 3 pi halves of this number. And all we need to know is that this thing here is a number. And that goes to 0 as kj goes to infinity, because this doesn't depend on kj. And kj over kj, something on the order of kj squared, goes to 0. And that means that our computation is mathematically clean, and we have computed the correct Laplace transform. Okay, if you think this was hard, you're right. This is hard. It took me quite a bit to figure out these estimates. I'm not sure if they're in the textbook already, but like I said, I'm a pure mathematician. I'd like to have everything signed, sealed, and delivered. If nobody asks you to do these kinds of estimates, then there is no need to do them. Of course, if somebody does ask you to do them, then there is no way around them. But what you can see here is that inverse Laplace transforms can be computed using consequences of the residue theorem. The run-of-the-mill Laplace transforms, if you're really good with residues, or if you have to work with residues a lot, ultimately are probably easier to compute using residues. And you can also compute some really nasty stuff, as we have seen here, using the formula for the inverse Laplace transforms. This concludes what we're going to do with the residue theorem. We're going to start a new section of the course where we're going to talk a lot about geometric type work. And well, until then, I think we all need a break. So let's take that break. You go ahead, handle some homework problems. The computations most likely will be epic. If worst comes to worst, ask me what you can do if you're stuck somewhere. It is entirely normal to have to spend a lot of time with this stuff because believe me, I have to. All right, I'll see you then.